Hello. In this video we're going to take a look at the hydrogen atom, one of the most important applications of quantum mechanics because it provided a full solution to one of the original experimental motivations for developing the subject. So the time-independent Schrödinger equation is as follows. So we have a kinetic energy term. This, rather than the electron mass here, this is the reduced mass of the electron nucleus system, where Mn would usually be the mass of the proton, but we could have deuterium, where we have a proton and a neutron in the nucleus, or tritium, where we have a proton and two neutrons, or we could even consider things such as positronium, where you have an electron-positron pair in a bound state. So that's the kinetic energy term. The potential energy term is due to the electrostatic attraction between the electron and the nucleus. So it's describing the behavior of the electron in the hydrogen atom. We can see that we have bound states. We have negative potential for all values of R. So we have an infinite set of bound states in this system. And we have a spherically symmetric potential. So let's write those two things down. The fact that we have a spherically symmetric potential means that we can bring to bear all the tools we developed in the previous video where we studied such cases in generality. So let's take a look at the solutions here. So we can substitute an ansatz of the form chi as a function of r divided by the radius r, multiplying the spherical harmonics y(l)m as a function of theta and phi. Substituting it in, we get the following form. We can simplify a little bit by defining some new constants. So we can define the Bohr radius, or rather the reduced Bohr radius. If this mu were the mass of the electron, this would be the Bohr radius. It's a length scale appropriate for the system. And using this, we can define a dimensionless radius, r over a naught, and a dimensionless energy scale, given here. If we substitute these back into the equation, we get the following, where I've slightly redefined chi so that it's now just a function of rho. So this equation, remember the way to try and solve such ordinary differential equations is to massage them into a form where they've already been solved. In this case, we can do this by looking at different limits. So we can look at the case that r is very large, or sorry, rho is very large. That is, rho is much greater than 1 because it's dimensionless. In that case, we lose this term and this term because they're divided by rho and rho squared respectively. Our equation becomes d squared chi by d rho squared is equal to lambda squared chi. And so the relevant solutions are chi goes as e to the minus lambda rho for rho much greater than 1. The other solution that we could have had would not be normalizable. In the other limit, rho is much smaller than 1. This term becomes significantly more important than this one or this one, and so our equation reduces to the following form, and you can check by substituting that this form will solve it. Chi is a polynomial, it goes as rho to the l plus 1. Substituting it into here, you bring down l plus 1 and l, and you get chi over rho squared, and that cancels with this term. So using these two limits, we can motivate another ansatz to transform our equation of the following form. So we bring the two different limiting forms out and multiply it by some unknown function and scale it by 2 lambda rho. And in fact, it's convenient to define a new variable. Let's define the variable y as follows. So it's 2 lambda rho is equal to y, another form of length scale. When we substitute this form back into our equation up at the top, we transform it into the following. So it may not look particularly nice, but it is an equation that has already been solved. We knew the solutions. This is in fact what's called Laguerre's equation. And in this case, the solutions are what are called generalized Laguerre polynomials, which have, written as capital L, they have two indices. The lower one is n minus l minus 1 in this case, the upper one is 2l plus 1, and in this case a function of y. So these generalized Laguerre polynomials, you can find them from the following formula. So you can substitute in the relevant parts, and these generalized Laguerre polynomials are orthogonal to one another, where orthogonality for these functions is defined as an inner product here with a weight function defined to be y to the alpha e to the minus y. And in this case, these ones aren't normalized, they have this prefactor. So they're labeled by two labels, and in those labels are two quantum numbers. L we've seen before, it's the azimuthal quantum number. N we're seeing for the first time, and it's what's called the principal quantum number. So n is an integer and it's greater than 0. It's called the principal quantum number, and the form of these solutions, the generalized Laguerre polynomials, actually places a limit on L, which we didn't have before, of the following form. So L, again an integer, but it must be greater than or equal to 0, but it must be less than n. So there's an additional constraint coming from the form of these solutions. If we take a look at the original equation, the full solution, we get this. So original time-independent Schrödinger equation, here written in Dirac notation. The eigenenergy En is given by this. These form of 1 over n squared with some prefactors actually matches the Bohr model of the atom that we saw at the very start of the course. So that was a kind of phenomenological guess. This is now the full solution to the time-independent Schrödinger equation, and it matches Bohr's guess. And the eigenstates, NLM, take the following form, projected into the position basis and the spherical polar coordinates, which is admittedly rather complicated, but you can substitute in values of n, l, and m and find the corresponding wave function which solves the time-independent Schrödinger equation. So we have three quantum numbers hidden in here. N, L, and m are all integers. N, which is greater than 0, is the principal quantum number, but more specifically, it's the shell of the electron. So we can be in shell 1, 2, 3, and so on. L, the azimuthal quantum number, is really the orbital of the electron. So they have special names for the different values of L. So we call L equals 0, 1, 2, 3, etc. S, P, D, F, G, and then I think it just continues H, I, J, etc. So these are old-fashioned names that don't really mean much anymore. I think it's sharp, principal, diffuse, fine, G, H, I. They are meaningless after that. And so, for example, in the n equals 1 shell, the lowest shell, we can only have the L equals 0 case. We can only have the S wave case or the S orbital. In n equals 2, we could have L equals 0, so we can have an S wave, or we can have a P. Sorry, we can have an S orbital, or we can have a P orbital. And this is how we build up the periodic table. And finally, we have M, which ranges from minus L to L, and is called the magnetic quantum number for reasons that we won't really go into in this course. But it's the Z projection of the angular momentum. Okay, so if we take the n equals 1 shell, L must equal M must equal 0, and the wave function is proportional to, with some real constants of proportionality, e to the minus r over a naught. So if we plot the probability density of this function as a function of r, we just have an exponentially decaying probability density. And if we were to plot a surface of constant probability density, it would look like this. So it would just be a spherical shell. If we were to request that the modulus square of this with its prefactors is equal to some specified constant, then it'll be a sphere for whatever value of c we choose. If we look at the n equals 2 case, let's take the n equals 2, L equals 1 case, and we'll choose m equals 0 to start with. It looks like this, again, omitting the constants of proportionality. If we plot the modulus square as a function of radius, we see that the modulus square of this must increase as r squared towards r equals 0, and then it must decay exponentially again out towards r tending to large values, so we have a hump and then a decrease. And so if we were to plot a surface of constant probability density, it would look like this. So when cos squared theta, because we need to modulus square this, when theta is 0, that is up at the top, or when theta is pi at the bottom, this is a maximum in theta. And we see that it must be 0 towards the bottom here, and so it must be something like this. So two bulbs along the z-axis. And if we look at the case n equals 2, l equals 1, m equals 1, the radial dependence is the same as the previous case, so it looks like this again, but we now have a different angular dependence. And when we take the modulus square, the phi term doesn't contribute anything, it only gives a complex phase. But in terms of theta, we find the result, which is my attempt at drawing something a little bit like a donut. It doesn't vanish exactly in the middle, it vanishes at 0. When r goes to 0, this goes to 0. It increases as a quadratic away from 0, but now when theta equals 0 up here, or theta equals pi, it's 0, reaching a maximum down in the z equals 0 plane. So it's a bit like a donut. It sort of spreads out to a thick donut, but the donut's not actually it's got a very tiny hole right in the centre. Okay, so those are some of the solutions, and you can work out others yourself. Thank you very much for listening.